Hello guys, I'm Deepana Govindaraja. By the way, the topic we are going to see today is Kubernetes. Do you think what is Kubernetes? Why we need Kubernetes? Kubernetes is one of the orchestration tool. So you might have the question, what is then orchestration? Orchestration is a tool that abstracts away the complexities of deploying and managing individual containers by providing a high-level interface for managing containerized application as a whole. So you might think an application which have thousands of microservices. So each microservice is pushed or worked inside a separate container. So you have thousands of containers. So you need to maintain thousands of containers separately. And communications between them become also difficult. So Kubernetes provide an orchestration tool. So we can make thousands of containers as a whole. So it provides a high-level interface for managing these thousands of microservices. In addition to that, in this overall application, we can able to scale up the microservices. That means scale up the containers, and also able to monitor the health of the containers and able to restart them if they fail also. So these are the benefits of the orchestration tool. If we discuss detailedly, as I mentioned, orchestration tool helps to scale it automatically according to the demand or traffic. And also, it provides a self-healing and fault tolerance. So that means it will monitor the health of the containers and automatically restart the failed containers or replace them with new instance. And also, it has the ability for the resource management. That means we can able to define separate namespaces, and within the namespaces we can able to define the resources. So we can make sure each containers has the required resources in order to have the application. And also it has the built-in service discovery. And also we are abstract away the complexity of managing individual containers, because orchestration provide a high-level interface for managing as the whole application. And also it has the portable ability, and also it has the load balancing. That means we can able to maintain the distribute the traffic to all the microservices equally. So if you see the container orchestration tool, we have Docker Swarm from Docker, Kubernetes from Google, and Mesos from Apache. Since Kubernetes is from Google, it is written on the Go language. Among these three orchestration tools, Kubernetes is the most popular one because it has a lot of options for customization, and it has the huge support from popular vendors such as Google Cloud Platform, Amazon Web Services, and Microsoft Azure. If you think Google Cloud Platform, it provides feature for GKE, that means Google Kubernetes Engine. It abstracts away the underlying technology of managing individual worker nodes, master node. It gives the interface. Overall interface. So we don't need to deal with the underlying technology. And if we think what is the relationship between Docker and Kubernetes, Docker is the containerized application. That means each microservices is pushed inside the Docker. And Kubernetes is the overall technology to provide the orchestration platform to manage and automate the deployment of containers across the cluster. Docker is often used to build the container image that Kubernetes then orchestrates and manages in a production environment. So now let's see what are the main components of Kubernetes. First one is the pod. As I have mentioned, Docker is the Kubernetes. So sorry, Docker is the container. And here what we need to do is pod provided execution environment for the containers in the Kubernetes. That means it encapsulates one or more containers and provide them with a home and IP address. That means within the single pod, there can be one or more containers, and each pod has the single IP address. And these are see every containers, and this is pod. And containers within the pod can communicate with each other using a local host because IP address is common for the pod. So it make it easier to manage multi-container application. And since it provides an execution environment for containers, we don't need to deal with the containers directly. So we don't need to deal with directly dealing with underlying container technology such as Docker, because containers are Dockers. So if we don't have the pod, we should know how the Docker work also. And in the pod can die very easily. As I have already mentioned in the benefits of the container orchestration, it provides the mechanism for self-healing and fault tolerance. That means it monitors the health of the containers and automatically restart or replace them with new resource. So these pods can be easily done. So when the pod crashes or become unresponsive, what we'll do is Kubernetes will automatically restart the pod or reschedule it onto a healthy node. As we have already know, one common IP address is given for the pod. When the pod is replaced, it will receive the new IP address. So, since it is receiving the new IP address, it can become inconvenient if you are relying on the static IP address for communication. Because when you're restarting it, every time you need to adjust the IP address as well. So, in order to overcome this challenge, you are providing the concept of service. So, service is an abstraction that provides a stable network endpoint. Stable network endpoint in the sense it's an IP address and a pod for accessing a pod. Because as we have already mentioned, when pod is restarting, it will be given with a new IP address. So communication becomes problem. In order to avoid this, we introduce the concept of service. So in the service, what will we do is, during the communication, we have given a static IP address. And with the service, it maintains an internal mapping of IP address and the ports to the ports. So it automatically updates the mapping when ports are created, stale, or replaced. So we don't need to update the IP address every time when we restart the ports. Clients can communicate with the service using its stable IP address and port, and the service will route the traffic to the appropriate ports behind the scene, eliminating the need to adjust the IP address every time the port restarts. And if we see ingress, ingress is an API object that defines rules for routing external traffic to services within the Kubernetes cluster. That means traffic can be from the internal cluster. That means there can be many ports. So we need to communicate between the ports. And also there can be external traffic as well. So ingress helps to define rules for routing external traffic to services within the Kubernetes cluster. And ingress is mainly used for routing of HTTP and HTTPS services. And for others, non-HTTP or non-HTTPS methods, we will use other services such as Node and such kind of things. It is for HTTP and HTTPS external traffic to direct within the Kubernetes cluster. So in the Ingress, there are many Ingress controller like Nginx, Traffic, HAPoxy, like those are the examples for the Ingress. And the fourth component is the config map. Config map used to store the configuration data, such as the database connection string, environment variable, command line arguments. Within these are the configuration data. So these configuration data are stored in a config map. Config map are stored as a key value pairs. The benefits of having config map is they can be used to decouple the configuration data from the application code. For example, we have the database string in the config map. If we insert the database string with the application code, what we will do is when we update the database string, we need to redeploy it or restart the application. So here we have separate config map file. So which make it easier to change the configuration settings dynamically in the real time without restarting or redeploying the application. The fifth component is the secret. Secret is also similar to the config map, but the thing is here we store the sensitive information. Here also we store as the key value pair, like similar to the config map. But here we store the sensitive information like the password, API keys, tokens, certificates like TLS certificate, SSH keys, like those we have stored in a secret. So, secret provide a secure way to store sensitive data. Ensure that it is not exposed or transmitted in plain text within the cluster. Secrets are stored in an encrypt format in the etcd data store of the Kubernetes cluster. Access to the secret is controlled through Kubernetes role-based access control. So, this define fine-grained access policies, ensuring that authorized entities can read or modify the secret. But in the case of config map, it is public. Even unauthorized parties also can able to access it. But for the secret, we have encrypted and we are providing the role-based access control. So, the only authorized parties can able to access it. Secret also similar to the config map. That means it is decoupled from the application code. So we can able to update it dynamically in the real time without restarting or redeploying the pods. That means when a secret is updated, the changes are automatically propagated to the pods using it. There are different types of secrets. Opaque is the generic key value pairs. TLS used to store the TLS certificates. Docker registries, that means authentication credentials for private Docker registries. Like those, there can be different secrets. These are only examples. And the next component is the volume. Volume is an abstraction that provides persistent storage for containers running in a pod. That means in normally volume allows data to be shared and preserved across container restart, not failures and pod rescheduled. That means volume will be preserved. That means it will not destroy along with the pod. Volume can be also used to facilitate communication and data sharing between containers running in different pods. By sharing a common volume, multiple pods can read and write data to a shared location. There are three types of volume. One is ephemeral volume, second one is persistent volume, and the third one is claim volume. Here in the first one, this is created and destroyed along with the pod. That means it will not be persisted when the pod is restarted or deleted. So it's a good choice only for the temporary data, such as logs. But in the persistent volume, it will It will not destroy along with the pod. So data will not be lost when the pod is restarted or deleted. So it is the good choice for storing permanent data, such as databases or application data like those. And in the case of deployment, it is a declarative way to define and update the desired state of your application. That means you need to run 5 pods. Like those, you are declaring your desired state of your application, ensuring that the specified number of replicate the pods are running and available. As I mentioned, 5 pods are running. Like those, you are specifying your desired state of your application. Deployment can help you ensure that your application are always running with the desired version, and they can be scaled up or down as needed. So deployment always ensuring that your application is running in the desired version, because you are mentioning the desired state of your application. So benefits of using deployments, it's a declarative update. That means you can able to specify the desired state, and it checks whether your application is in the desired state. Kubernetes will take care of updating the actual state to match the desired state. So this makes it easy to roll out new version of your application without having to worry about manually updating ports. So that's a case in the automatic scaling as well. So according to your demand, you can able to scale up and roll back. If the deployment update fails, you can easily able to roll back to the previous version. So in the previous sector, we have seen about the services. So when the pod fails, it will gain a new IP address. So in order to prevent updating the static IP address, we introduce the concept of service. So it provides the stable IP address for the communication. And also it acts as a load balancer, so distributing incoming requests to available ports based on the defined load balancing algorithm. On the other hand, deployment is a high-level abstraction. That means it manages creation and scaling of replica pods instead of directly creating and managing individual pods. That means you will define a blueprint. Like in developing, you have seen the concept of blueprint for the object. So from the blueprint, you are creating new objects. Like that, here also similar concept. In the blueprint, you are specifying the desired state of your application, like the number of replicas, container images, resource requirement. And the deployment controller. Here, there are controller like replica set. Like those, deployment controller ensures that the desired number of replica pods are running. By using deployment, you can easily scale the number of replica pods up or down. That means you can able to roll out the new versions or roll back if the previous version, if the new version fails. And then the final component, main important component is the stateful state. Stateful state is used to manage the stateful application, where each pod has the unique identity, persistent storage, ordered replicas, and stable network identity. So, in the stateful state, ensures that pods are created and deleted in the correct order. When a new pod is created, it is assigned to the next available original index. When a pod is deleted, a stateful set controller ensures that the next pod in the replica set is not created until the deleted pod has been terminated. So some examples of stateful application that can be deployed using stateful sets. Examples, first one, database such as MySQL, PostgreSQL, MongoDB, message queues such as RabbitMQ, Kafka, distributed file systems such as Gluster, FS, and Ceph, and also key value store such as Redis and Dynamo. Now let's see about the main components in the Kubernetes. That means Kubernetes architecture. There are two types of node. That is, first one is the master node and the second one is the slave. That means worker node. If we see the concept of worker nodes first, worker nodes where the containers are scheduled and run. These are the nodes do the actual work. The second master node only provides the centralized management. So within the worker node itself only, containers are scheduled and run. They form the execution environment for the application deployed in the cluster. Each worker node hosts multiple pods, which are the basic units of Kubernetes. As we have already seen, pods provide the execution environment for the containers. That means pod encapsulate one or more containers and provide a common IP address. But here in node, every single node, there can be multiple pods. Since pods are the basic unit for Kubernetes. Worker nodes are managed by the Kubernetes control plane. That means master node, and preprocessors must be installed on every worker node. As we have seen, there is worker node and master node. With every worker node, there are preprocessors. First one is Hublet container runtime and the Hub proxy. If we see Hublet, as we have seen, installed on every worker node and is responsible for managing pods. That means it is manages the life cycle of volumes associated with pods, bring up and managing pods on each node, pulls container images, monitors the state of pods, monitor the health of pods, scale pods up or down automatically. The second component is the container runtime. Container runtime is responsible for managing and executing containers within the pods. Popular container runtimes are Docker, contained, CRIO. So it is responsible for creating and starting containers, monitoring the container health and restarting them if they fail. Stopping and deleting containers when they are no longer needed. Container networking. As we have already seen, Hublet is used for managing the health of the pods. That means monitors the health of pods, scale pods up or down automatically, monitors the state of pod. But container runtime mainly deals with the containers. That means stopping and deleting, creating and starting, monitor the health, container networking. Container networking in the sense it sets up the networking configuration for containers, such as assigning IP address, managing networking interface, and enable communication between containers and external service like those. And in the case of container runtime abstracted by the container runtime interface, CRI serves as a standardized API that allows Kubernetes to interact with various container runtimes seamlessly. Kubelet, which runs on each worker node, is responsible for managing pods and their containers. It communicates with the container runtime using CRI. Since CRI abstract away the container runtime. So, Kubelet communicates with the container runtime using CRI to create, start, stop, and manage containers. Since container runtime manages the containers like starting, deleting, stopping, like those terms. So for the Hublet, instructions are received from the control plane. Then Hublet relies on the container runtime to handle low-level container operations. And the third one is Hube proxy. Hube proxy provides the benefits such as service discovery and the load balancing. In the Hube proxy, there are four modes like IP tables, IPVS, user space, and kernel space. User space is deprecated in the Hube proxy, and now it's not being used. IP table is the default mode, and it creates IP tables to forward traffic to the ports. IPVS means it creates rule to forward traffic to the ports. And in the case of master node is responsible for managing and coordinating the entire cluster activities. So it overseeing tasks such as scheduling ports, maintaining cluster state, managing scaling, and handling cluster-wide application. So it main role is provide centralized management. As we have already seen, there are some components installed with every worker node. They are Kube proxy, kubelet container runtime. Similar to that, every master node contains the following four components. They are Kube API server, Kube control manager, etcd, Kube scheduler. Cube API server, in the sense it is the front end for the Kubernetes cluster. It provides the RESTful interface that allows user to interact with the cluster. It acts as a gateway for user and application to interact with the cluster and handles authentication and authorization and also validate the request. Clients can communicate with the API server using command line tool or Kubernetes dashboard. In the Docker Swarm, we don't have such a dashboard. Then second one is the control manager, and in the case of control manager, it is responsible for managing and running various controllers that handle different aspects of the cluster. First one is the node controller. It monitors the state of nodes in the cluster, detect node failure, changes, and takes actions to maintain the desired number of available nodes. Nodes means it's the working machine. And job controller handles the execution of the task. Replicas, and it ensures the specified number of ports replicas are running. The deployment controller manages the life cycle of the deployment, creating new replicas, scaling them up or down. Service controller monitors the creation, modification, and deletion of service. So in the case of controller manager, each controller within the controller manager follows the reconciliation loop. It continuously compares the desired state of resources as defined by users or system configurations with the current state of the cluster. If there are any discrepancies or changes, the controller takes appropriate actions to bring the cluster to the desired state. That means it checks whether the desired state and actual state are same, and if there are any difference, controller takes appropriate actions to bring the cluster to the desired state. So, controller manager operates in an event-driven architecture. That means it watches the changes in the cluster state by subscribing the relevant event. When an when an event occurs, the corresponding controller triggers the necessary action to reconcile the state. And the third one is the scheduler. Scheduler responsible for placing newly created pods on the suitable nodes in the cluster. So its main function to ensure resource utilization and high availability by considering factors such as resource requirement, node capacity, affinity, or anti-affinity rules. Affinity rules means define the preference of running nodes on the same nodes, and anti-affinity rules define the pods that cannot be scheduled on the same node. So, Kubernetes allows user to replace or extend the default scheduler with custom schedulers. The scheduler is implemented as a set of plugins responsible for different aspects. First one is scorer. Scorer plugin calculates the score for each node eligible to run the pod. The score is based on pod's requirement, node resources, and the node scheduling process. Filter plugin filters out the nodes that do not meet the pod resource requirement or scheduling policies. And the binder plugin binds a post to the specific nodes. etcd is a distributed key values store. As we have already seen, config map and secret are stored in the etcd as the key value pair. That persistent data store for storing and observing critical configuration data, state information, and metadata for Kubernetes. It is a distributed database designed to be highly available and reliable. It uses a distributed draft consist algorithm to ensure data consistency and availability even in the presence of node failures or network partitions. Now let's see about the Minikube. Minikube is the tool that enables developers to run a single node Kubernetes cluster locally on their machine. So it provides the convenient way to set up and experiment with Kubernetes without need for a full-scale production cluster. So Kubernetes creates a single node cluster, which means that all Kubernetes components, including the control plane and the worker node, run on a single machine. This configuration is only suitable for local development and testing scenarios. Minikube can be configured to work with different container runtimes, including Docker, container, and CRIO. Minikube runs Kubernetes on your local machine by utilizing virtualization technology or hypervisor. kubectl is the command line tool used to interact with Kubernetes cluster. kubectl is installed with every Minikube, so we don't need to install it again. So if you see the basic commands, listing resources in a cluster, that is kubectl get pods, get nodes, like those. Creating Kubernetes components, it is kubectl create, but in practice you will not create pods directly. Since we will, as we have already seen, we will create the blueprint, that is deployment, and that will create the pods underneath. So we will create the blueprint deployment. So here, kubectl create deployment nginx, image nginx, and replicas tree. So here we state we are creating uh, deployment named nginx, and here containers. Nginx is pulled from the Docker Hub, and we will create 3 replicas. Yeah, since we are creating here, we will get the auto-generated configuration file. But in practice, you will usually work with the Kubernetes configuration file because it's impractical to write all the options in a command line. So creating the configuration file. So creating the configuration file, we will write this command, and in order to describe the information about the specific resource, kubectl describe pod, my pod. My pod is the name of the pod. Then retrieving logs about the specific resource, that is kubectl logged my pod. Here we will not mention the pod. kubectl logs my pod, but here kubectl describe pod my, then the name. And applying changes to the source file ubcd apply. Here we will create. Here we will apply the changes. And deleting a resource, here also we are mentioning pod or deployment. Thereafter name. Only logs, we don't need to mention the pod or deployment. And configuration file. Configuration file is a YAML file. It mainly contains two-part metadata and specification. Metadata information about the object such as name, namespace, and label. Specification contains the properties, and the specification section vary according to the type of the object being created, like deployment, service. According to the type, specification sections varies. Additionally, rather than these two, metadata and specification, there is another section called status, which is automatically generated by the Kubernetes and contained information about the current state of the application. So Kubernetes continuously compare the desired state specified in the configuration file with the actual state of the source. If there are any discrepancy, it will reconcile the difference to bring the resources to the desired state. And self-healing is the fundamental aspects of Kubernetes, ensuring that the system maintains the desired state. Despite failures or changes. That means if any crashes or failure occur, it will automatically restart or replace. So in order to apply the changes or create, we will apply this command. And configuration files are highly customizable. That's why we are creating the configuration file rather than the going with the commands in the command line. Configuration files are usually stored with your code or in your own Git repository. So this is the example for the configuration file of the deployment. As I have mentioned, there are mainly two components, metadata and the specification. Specification section varies according to the type of objects created. So here we are creating the deployment. That's why for deployment section, specification is like this. So in metadata, we are specifying the name and the label itself. And in the specification, we are mentioning how many replicas we need and select and in the template again there is a metadata and the specification. This is the example for the deployment configuration file. It has another template with the metadata and specification which describes about the pod. So this is the specification for the pod. So here in the pod, it will run the container name my container and it will pull the image nginx and it will export the port of 80. So this is the example of the configuration file for the service. Here also metadata and the specification. And in the specification, in the selector section, you will mention the name with which port, with which deployment it is connected. So here, the same app my name. So the same name will be given in the selector section if that port is connected with the service for redirection. And here it will say for which port we need to forward the details. And this is the port which is exposed. And this is the type of service. Default is the cluster IP. Cluster IP allows only the internal traffic. It will not allow the external traffic. There are other types such as node port. Node port allows the external traffic, but it will not perform any load balancing or functions. So it is only used for the development process, and in the deployment we will create the external service for allowing the external services with the load balancing. So this is how configuration files works. And if we have already seen, for storing sensitive data, we are using the secret, and this is how we will create the secret with metadata. And here we will mention the type opaque. As we have already seen in the secret section, there are different types such as opaque, TLS. TLS for storing TLS, and Docker for separate for the serving the Docker registry credentials. So here, what we will do is creating the secret YAML file, and it contains the username and password for the database. So here the thing is, we need to create the secret before creating the deployment, because it relies deployment relies on the secret. So order of the creation is very important. So in the deployment section, we are referencing the secret here. Environment, name, username, value from secret key ref, name, my secret key, username. Like that, password also referencing. Config map also same thing. So here also we need to create before the deployment if it's depends on the deployment, and here we are referencing. And in the service, as we have mentioned, there are different services like cluster IP, node pod, external service, and the load balancing. So the default one is cluster IP. So the service is a logical abstraction for a set of ports. That means it defines a single point of access for a set of ports that are running on the same service. Regular service, that means cluster IP is typically accessible only within the cluster's internal network. It does not allow the external traffic. External services are created in order to allow for the external service. So when you create the external service, you specify an external DNS name as the service endpoint. So the DNS name could be an IP address, domain name, or valid network address accessible from outside the cluster. When clients access the external service, Kubernetes resolves the DNS name to the specified external address, allowing traffic to be directed outside of the cluster. So here to create the external service, we have given the external name, DNS name. So it will forward traffic to that port. And now we are going to see about the namespace. As we have seen in the benefits of the orchestration tool, we can able to define the resources required for the particular containers. So this is the namespace comes into play. Namespace is like a virtual cluster that provides a way to divide and isolate resources within the cluster. So it acts as a logical boundary or a virtual partitioning mechanism for Kubernetes object. So in order to create the namespace, kubectl create namespace, and to get available namespace, kubectl get. And there are four types of default namespaces for specific purposes. First one is default. It is the namespace where resources are created if no namespace is specified explicitly. These are the default namespaces: default hubs, hub system, hub public, hub non-release. Hub system is used for Kubernetes system components and infrastructure. It includes resources such as hub proxy, hub scheduler, hub controller manager, like those. Hub public, the namespace is accessible to all users, like authenticated or unauthenticated. So like example config member stored there, and hub node release It is used to track the heartbeat of the nodes in the Kubernetes cluster. Not the health of the pod, it is check the heartbeat of the node itself. Checks whether nodes are still alive or not. So, health monitoring system by tracking the heartbeat of the nodes, the control plane can ensure that the cluster is healthy and that all the nodes are available. So accessing resources on other namespaces, by default, resources within a namespace are isolated and cannot be accessed directly from other namespaces. We can mention the namespace directly in the configuration file itself. Okay, thank you. You can follow me for more posts in the LinkedIn. Deepana Govindaraja.